Thanking the organizers for the opportunity to speak. So my talk will be about a graphical calculus for what we call K-point quantum vertex operators. So this is actually related to what Jasper talked about last week. So what I'll be talking about is a quantum version of this. And so this is actually joint work with Jasper and also with Hadewijch de Clercq. So to give an overview, what I'll first be discussing is the existing graphical calculus. So this is what existed for what we call ribbon categories. Then I will say something about how we extended this to categories which have less structure, so namely braided monoidal categories with twist. And then I will apply this graphical calculus to certain categories of quantum group representations. And there we can then find quantum vertex operators and dynamical fusion operators. And this will then allow us to assign a dynamical parameter to the morphisms that we discuss. And finally, I will say something about twisted trace functions. Okay, so first ribbon categories. So these are in fact the categories in this talk that will have the most structure. So they are monoidal categories. So we have a tensor product which have braiding. So as we've seen last week, this gives us morphisms from tensor products V tensor W to W tensor V. Now our braidings will not be symmetric. So these things are not symmetric tensor categories. But what we do have is a twist automorphism. So these will basically in our quantum group give rise to central elements in the quantum group. So things that will commute with everything. And then we also have left duality. Giving rise to rigid structure on our category. So we have a way of assigning dual objects to our objects V. And correspondingly, we have left evaluation and left co-evaluation, which are the analogs of what we've seen also last week in Pavel's talk. Then one can show that if we have the combination of this braiding, this twist, and a left duality, then one also has what we call right dualities. So this means that with respect to the same kind of dual objects, we have also evaluation and co-evaluation, but with the orders of the objects and the duals reversed. Let me give you an example of such a ribbon category. So this is simply the category of all finite-dimensional representations of a quantum group UQG. So we'll fix UQG to be any quantum group with G a semi-simple algebra, and we fix H to be a Cartan subalgebra inside G. So what do we have in this case? Then we can take our braiding to be simply the action of the universal R matrix together with B, which is just a flip automorphism. So sending A tensor B to B tensor A. And then in this case, we can take the twist to be the action of Grinfeld's ribbon element. So this is an element actually in a completion of the quantum group, which can be constructed from multiplication of the inverse R matrix with the inverse antipode acting on one of the two legs. And this q to the power 2 rho that appears here also is so an element in our Cartan subalgebra where rho, as was said also just a few minutes ago, is just 1/2 of the sum of all positive roots. And then left duality is simply what we're used to already. So left evaluation is really evaluation of the dual vector element on the vector. And co-evaluation is just sending the scalar 1 to this sum, where we actually sum here over this BV. What we have here is actually a homogeneous basis. So basis consisting of weight vectors of our module V, which is necessary in order for this thing to be actually linear for the quantum group. And then we have right duality. And then one could say, okay, can we just do the same thing as before, but with reversing the orders of duals and simple objects? But this does not work. So if one would just, okay, we send V tensor F to F acting on V, well, this would give us something that is not linear for the quantum group. So we really need this extra q to the power 2 rho element to make this UQG linear, and similarly for co-evaluation. So this is really something where that is not visible in the classical case, but it's really important in the quantum case. So what do we then need? We will need stratification of categories. So this is a well-known theorem by MacLean saying that every monoidal category is tensor equivalent to a strict monoidal category. And he gives an explicit construction for this. So as objects in this strictified monoidal category, we'll take just tuples of objects in our original category C. And if we have a tuple of length 0, this actually just means the empty set, empty tuple. And so then morphisms in the stratification will simply be defined as the morphisms in the original category between the objects corresponding to the VI or WI objects which we just tensor together. And tensoring in this case always means that we tensor basically from right to left. So we just first take VK minus 1 together with VK, and then we go from there on to the left. So this is the fixed order that we always take. But so the idea of taking strictified monodal categories is actually to be able to forget about this ordering of the tensor product. And then we'll take this box as a new notation. So for the tensor product in the strictified category, which is just concatenation of objects, and we'll denote by f strict this tensor equivalence that we have. It's basically sending tuples to the corresponding multifold tensor products. Essentially, nothing is going on there. You don't actually do something spectacular when moving from monodal categories to strictified monodal categories, but it's really in the graphical calculus that these things will become important. So then what are the building blocks for our graphical calculus? So the basic things that we always have is that we'll represent these morphisms A, so between two tuples, in our strictified category, like these boxes labeled by A. So we'll always read our diagrams actually from bottom to top. And then for certain morphisms in our category, we will need special notations, special graphical notations. For example, for the braiding, we have this overcrossing. For the inverse braiding, then we get an undercrossing. For the identity morphisms on duals, we will have the convention that these are depicted by arrows going upwards. This is actually something non-trivial because what we have in the quantum case is that taking double dual, so V dual dual, is actually not equal to V itself. So there should, I'm not going to go into technical details here, but in our paper we describe why we can actually do this assignment of arrows labeled upwards with these duals without giving contradictions with these double dual theorems. Okay. And then if we have that, we can also use cups and caps then to denote precisely these evaluation and co-evaluation morphisms. And the way in which they are oriented tells us whether it's a left or a right duality. The actual assignment between morphisms and diagrams is through the Richteken-Derive functor, so which is a functor from this category of C-colored ribbon graph diagrams to precisely our strictified category corresponding to the ribbon category C. So there's actually many versions of this functor around. I think the version in Derive's book is actually different, which starts from the strictification already inside the category of ribbon graph diagrams. But it will turn out that, well, this version is actually the most useful for our purposes, where we try to extend this to categories with less structure. Okay. We, of course, then also have certain local topological moves that we have to take into account, for example. So the first one that we have here, this is really saying that, well, our braiding really satisfies the quantum Yang-Baxter equation. And we also have these ones, so with the twist. So these will basically be the diagrams for our twist automorphism. And so there's several ways of actually depicting those. So either with the loop going to the right or to the left, and several ways also to do the same thing with the inverses. So basically these equalities tells us which ones are the duals for which loops. And then an example of such a diagram in total will then be as follows. So here we see everything. We see braidings and cups and caps. It's just an example of what one can do with this. And now what we would like to do is to extend this actually to Verma modules, but this actually gives a problem because categories of UQG representations that contain Verma modules for our quantum group will never be ribbon categories, simply because duals to our Verma modules will not be Verma modules for the same Borel subalgebra. They will actually be Verma modules for the opposite Borel subalgebra. This gives problems with the definition that we have for our original ribbon categories. So we'll need to extend this to larger categories which have, in fact, less structure. So these are then braided monodal categories with twist. So they are similar to the ribbon categories, but we no longer have duals. So no left duality, no right duality, but we still have the twist automorphisms. So as an example, we take this category. So introduce this category to be, well, category of all quantum group modules which still have all these properties. So they are not finite dimensional, but still they are the direct sums of their own weight spaces and so on. And so all their weight spaces are finite dimensional. So they still have a lot of nice properties. And these in particular contain all of the Verma modules. So we'll denote by M lambda the Verma module of highest weight lambda. And they also contain in particular the VGG category O, well, it's quantum group analog as a subcategory. So this category is then still braided monoidal. and we still have this twist. So our building blocks will be the same ones as before, but now without the duals, without cups and caps. But what we have is we still have the twists. So we'll still denote these twists with these loops like we did before. But the important thing now is that, well, one could write down these loops as well for ribbon categories. But there one could actually decompose them in terms of braidings, so crossings, undercrossings, and cups and caps. Here we really have to consider them as single objects. Well, single diagrams that cannot be decomposed any further. An example of such a diagram is this one. This could also be interpreted then as a diagram of ribbon categories, but the other way around, of course, it doesn't hold. So this assignment between morphisms and diagrams is now through a modification of the Dirichlet-derived functor that we've written down in our paper as well. So this BC here is then precisely the category of all what we call C-colored ribbon braid graph diagrams. And with this notation, one then has a more functorially adapted way of saying that two diagrams are equivalent. So we say that two diagrams L and L prime are dot equivalent precisely if they have the same image under this modification of the Dirichlet-derived functor. And it's in this sense that one can do the conventional way of saying, okay, composition is just stacking two diagrams on top of each other and taking tensor products, it's putting them next to it. We have one last thing, which was not really yet present in the existing graphical calculus, which is a notion of fusion. So this really goes back to the definition of morphisms in our strictified categories. So we can say, okay, we can consider a morphism in a strictified category between S, which is a tuple of length K, and going to a tuple of just length 1, consisting precisely of this multifold tensor products of all the VI objects. And okay, by definition, these are just morphisms in C between this multifold tensor product and itself. So there we can just take the identity. So this means that these fusion morphisms are actually trivial algebraically, but if we look at them in this strictified categorical context, then they are non-trivial simply because they go from an object of length K to something of length 1. So this will be our graphical representation for an object of length K. And so the one that we have here, so is the inverse version. So this is fusion JS and this is inverse fusion. Okay, and it will become clear later on why we actually need these fusion morphisms. And so, well, the advantage of this is that this actually allows us to reduce a lot of diagrams with parallel strands to diagrams where there's simply one single strand. So we know, for example, then at this one, where we have braidings, in fact, with parallel strands, actually is the same thing as just a single braiding on the multifold tensor product, where we have the additional fusion and inverse fusion morphisms on top and on the bottom.
I have a question, maybe a couple of questions. But this category you mentioned, this M admissible order, how is it different than category O? This category of quantum group difference?
It's not finitely generated.
Okay. And this twist guy, where will it so somehow usually this twist comes up when you want to use this Hadewijch 1. Here I guess you won't have any Hadewijch 1.
Indeed, yeah.
So this twist guy is just like in the graphical calculus, does he have satisfy relations?
Well, the only relations that we have are the ones like before where
so there's no relation that involves both the twist and the braiding and the crossing.
There are relations, yes. Those will be the relations that describe the tensor product. So the action of a twist on, say, V tensor W will be precisely through, well, to taking two braidings and then two twists on the separate lines.
Oh, okay.
Okay. I will show an example of that later.
So is that like a, okay. So it's a little bit like this Hadewijch 1.
Well, the Hadewijch 1 would say that it's trivial, but here it's certainly not trivial. But it has this nice action on the tensor product. So now let us apply this to what we call quantum vertex operators. So for this, so we'll need a bit of notation. So we'll say that a weight lambda is a regular or generic weight, well, if it precisely satisfies this property. And we'll denote by m lambda a fixed highest weight factor in the Verma modulo of weight lambda. So then there's this well-known theorem called the expectation value isomorphism theorem that tells us that, well, if we have V, any finite-dimensional quantum group representation, and lambda is a generic weight, then one can write down this isomorphism from, well, precisely, well, mapping, say, a tuple of UQG intertwiners between, on the one hand, a Verma module, and on the other hand, another Verma module tensored with our finite-dimensional module V. And so it maps onto the space V itself precisely by taking highest weight components. So you insert your highest weight vector here, and then you get something in m lambda minus mu tensor V. So you take a dual vector of the corresponding highest weight vector there. And so this will no longer be, so it's not an isomorphism of quantum, well, it's not an isomorphism of UQG modules, of quantum group modules, because on the space of UQG intertwiners, one cannot impose a UQG action, but it's they are, both spaces are still vector spaces graded by the dual of our carton, and so in this sense, they are really isomorphisms. One can take, of course, then the inverse of this isomorphism. So this will be the map which maps the vector V to what we call phi lambda V. This will be an example of a one-point quantum vertex operator. And so in particular, if V is actually a weight vector, then this phi lambda V is a single UQG intertwiner. So from our Verma module m lambda to the Verma module m lambda minus mu, where mu is the weight of our vector, tensored with V. And then it precisely sends our highest weight vector to the corresponding highest weight vector tensored with the vector V plus some lower order terms, by which we mean actually terms which are of lower weight in the Verma module and of higher weight in the finite dimensional module. So the total weight will always be preserved. And then, of course, these sums that we get in this way are finite sums, because our representation V is also finite dimensional. And then so the k-point analogs of these, so k-point quantum vertex operators, are then constructed by compositions of these one-point vertex operators. This is similar to the constructions that we've seen also last week in Jasper's talk. So what we do is we say, okay, we have k different finite dimensional modules. In each we take a weight vector, and then we take first phi lambda vk. So we go from m lambda to m lambda minus the weight of this vk vector. That's a space vk. And we say, okay, we'll leave vk invariant. We'll apply another one-point vertex operator. So then it goes again to another Verma module, tensor vk minus 1, tensor vk, and so on. So we put all of these together. So these will be our k-points quantum vertex operators. And the ones that we'll actually work with are the strictified versions of these. So they are precisely morphisms in the strictification of the category M admissible, corresponding to these small letter phi lambda v1 vk that we have. Okay, so algebraically they are just the same object, but it's actually the ones on the last line that we'll be able to represent also graphically. The notations that we introduced for these are as follows. So we wanted a way to distinguish between modules and finite dimensional modules. So we say, okay, we'll color the module lines in red and the finite dimensional lines in black. This is precisely because in the graphical calculus for the black lines, one can do more, one has more building blocks for the graphical calculus there than for the red lines, because we have dual for the black lines, but we don't have red lines. The second thing that we did is we rotated these diagrams over 90 degrees. This is simply because otherwise diagrams tend to become very long in the vertical direction. And there's a second reason, which will become clear when I show you the diagrams for the actual k-point vertex operators. So a different diagram that we can draw for this is just where we replace these parallel strands labeled by V1, Vk by one single strand labeled by S. And then, so what we do for really these k-point vertex operators, we introduce these notations really reminiscent of the fact that we have these different expectation values, so these different vectors Vi. So here we see that, okay, this should really be interpreted, be read as a diagram from m lambda, so to m lambda 0 tensored with all of these Vi's. So it should be read from right to left. And so we label the expectation values here in blue. And what we'll try to do with the graphical calculus is we'll try to find a way of pushing a morphism which is present somewhere here in the black lines, actually onto something which acts on these blue lines. So onto a morphism only acting on the expectation values. And then, so what one can do with this graphical calculus is, for example, proving what we call topological operator q-KZ equations. So these are equations which tell us that, okay, if we take these k-point vertex operators and we take certain gradings, both only on the finite dimensional representations as well as on combinations of finite dimensionals with Verma modules, and we take quantum trace over one of the different representations vi, this is equal to our k-point vertex operator, again, with some gradings. The algebraic version of this is not so important, but what is important here is actually the diagrammatic version of this. So in order to be able to prove such equations, what we do is we say, okay, if we take just a single vertex operator and we multiply it with this kind of scalar, this is precisely the scalar giving rise to the action of the twist on m lambda and inverse twist on m mu. So this is saying, okay, we take our twist or our quantum Casimir, we put it once here on m lambda and once the inverse on mu, and then we can use precisely this property of saying, okay, the twist on a tensor product is equal to a double grading together with two different twists, both on mu and on s. So the one on mu will cancel, and so this is what we get: a double grading together with one single twist on the finite dimensional module. And this is what we want to do, basically, with this graphical calculus. We want to get rid of all the difficult actions on the Verma module lines, such that all the complexity is, in fact, only contained in the finite dimensional modules. Because there, of course, we know, okay, everything will converge. It's all finite dimensional, so there it will work out easily. Okay, and then the last step here is that we say, okay, we have this line labeled by S here. We can just basically pull it through the phi intertwiner so that we get this loop all going around.
Isn't there a cap and a cup in the last diagram? Along the top line does that, but that was tilted by 90 degrees, so it's a cap and a cup.
This is really, yeah, this is a cap and a cup. Yes, indeed.
Okay, did he tell us that you had lost?
Only on the red lines, only on the Verma modules. Yeah, this is why we really want to push this to the finite dimensional ones, because there we still have cups and caps. Okay, so this is
Where did the two twists, those two red twists come from?
Because we have this scalar, so we know actually how the twist acts on Verma modules. So it's something like q to the power lambda in the product lambda plus 2 rho. It's always acts by a scalar since it's central. Yeah, so this is really the replacement of the two twists is the scalar that we put in front. Okay, then we can do the same thing with compositions of vertex operators. So the idea is that, okay, we put twists both here, and then we do the computation as on the last slide, and then we can basically pull pull the strand labeled by S2 all the way through both phi 1 and phi 3, so to get this. And so in this sense, you see that, well, there's not much spectacular going on with the red lines. Everything that is difficult is really in the black lines and the black strands. And then the final step is say, okay, choose precisely the correct multi-point vertex operators for these phi 1, phi 2, phi 3. Good. Then dynamical fusion operators can be introduced if we reduce our categorical framework, in fact, to something which has less structure even than the one that we considered before. So if you want to evaluate, say, in a certain vector M, or we want to apply dual vectors, then we'll simply say, okay, we'll just have our strand and in a circle labeled by this vector, or start in a circle labeled by this dual vector. Especially if we want to do this with highest weight, so with Verma modules, and we take the highest weight vector, then instead of always having to write the full circles with the full notations for the highest weight vectors, we'll just say, okay, we'll denote this by these small white dots. Now, one thing that one should be careful about here is that, well, since we are now working, since we have now applied boundary conditions, we have evaluated in vectors, we are no longer working in the category of UQG modules. We've actually reduced to the category of finite dimensional vector spaces created by the dual of our Cartan-Sub algebra. And this also means, for example, that now overcrossings and undercrossings for the braiding actually lose their meaning. The only thing that we can say is, okay, we have to, in fact, if we impose these boundary conditions, we have to replace all of the overcrossings and undercrossings by their algebraic definition, which is simply, well, the flip automorphism, which is a full crossing, together with the coupon labeled by the R matrix. So the morphism that algebraically means the same thing, but now still has a meaning in this graphical calculus. Also, for example, for right duals, what we now have is that, okay, if we take this, cap, which is oriented like this, well, in this reduced category, this only has the meaning of really saying we send V tensor F to F acting on V. So we have to explicitly put the coupon labeled by q to the power 2 rho there as well. We can introduce dynamical fusion operators as really the operators that send tensor products of vectors as of Vi to precisely the expectation value of the corresponding k-points quantum vertex operator. So really taking our k-points quantum vertex operator and taking here so the highest weight components again. Okay, so this is really considered then as a morphism in the non-strictified category. And again, we can assign also strictified versions to this, which we'll then note by J bar as lambda. So graphically, this would mean that, okay, we take our k-points quantum vertex operator, we take highest weight components. So these are the two dots. And then since we are here going from an object labeled by a tuple of length k to something which is of length 1, we have to take this additional fusion operator, this non-dynamical fusion operator, and put it on top. So really to get something which is of length 1. Something else that we'll need to do is we will need to know how actually the R-matrix interacts with these highest weight components. And this is in fact very easy, because what happens if we take the R-matrix and we have it act on the highest weight vector in our Verma module, then the only component of the R-matrix that will be left is the part which is in the Cartan subalgebra, because all the other ones will be of higher weight, acting, so of weight strictly positive, acting on the highest weight vector. And then, of course, this will give us 0 because there's nothing in our Verma module of weight higher than the highest weight vector. And then, so we get our Cartan term, and the Cartan term will act on this highest weight vector in such a way that we can actually replace this by an action of simply the Cartan element q to the power lambda acting on our Verma module. So this is an easy way of getting rid of the R matrices by, in fact, leaving additional markings on the finite dimensional modules. And then this can be used to prove topological q-KZ equations precisely for the fusion operators. So these are then of the form that, okay, in our left-hand side, we get the fusion operator together with a Cartan term, only acting on the finite dimensional modules. And on the right-hand side, we get fusion operators together with R matrices and also Cartan terms acting on the finite dimensional modules. So as you see, nothing non-trivial happens with the Verma modules. And so this can also be proven graphically. So we take our topological operator q-KZ equations and then we impose the boundary conditions. So the one that we have here then transforms to the one here. So we have to replace then all our overcrossings, undercrossings by their meaning with the coupons labeled by the R matrix. And then by using precisely this lemma, saying, okay, this thing will leave an additional marking on this S2 line and pulling, in fact, basically contracting the loop labeled by S2, we get something of this form. So where we see here, these were the markings labeled by the R matrices, which were left there by the R matrices, and we just get simply non-dynamical R matrices left on the finite dimensional modules. Okay, and then the last step is just taking again multi-point quantum vertex operators for phi1, phi2, phi3. So we get something like this. And then the only thing that we have to do is we say, okay, here we still have these new L weights which are present both here and here. We want to get rid of those, so we replace them by suitable Cartan elements in order to not have this explicit dependence on the weights of our vectors. In the special case where both k and I are equal to 2, then this is actually the ABRR equation, so named after these 4 people. And so this means that, well, the equations that we've derived in this graphical way are actually extensions of this equation. So this equation is actually the one that uniquely determines the universal dynamical fusion elements. And so we believe that similar statements should hold, in fact, for the k-point versions of the universal dynamical fusion operator. So then we will be able to assign dynamical versions, dynamical parameters to morphisms by means of these dynamical fusion operators. So for this, we have introduced a new category, which we call the dynamical module category, whose objects are simply the same ones as before, so are simply finite dimensional modules. and whose morphisms are now maps from the regular or generic weights to morphisms between our objects V and W, which are now considered simply as morphisms of H-star graded vector spaces. And as a tensor product, we take a non-trivial tensor product in the sense that, well, if A goes from V to W and B goes from P prime to W prime, we'll say, okay, if we take A tensor B acting on lambda, this will be the same thing as, well, B will just act on generic weight lambda. But for A, we get an additional shift, in fact, in our weight, which is precisely a shift by the weight which was present in the source space of the morphism B. Why do we define it like this? Well, precisely because this is how actually tensor products of dynamical fusion operators work. This is where we actually see this shifting of these weights showing up. And now for the dynamical fusion operators, we will then we will then introduce new graphical notations for them. So this will be a notation for the dynamical fusion operator. This will be inverse. And so if you put an additional label lambda, say here, then this will actually be, well, the dynamical fusion operator evaluated in the highest weight lambda. And here, what happens actually is that if you put your weight lambda here, then the weights will always shift when we pass, in fact, through a blue line. So here we get lambda minus the weight of Vk. And this is how you see that actually graphically the special definition of the tensor product is already incorporated in the graphical calculus. And then we introduce what we call the dynamical twist functor. So this is a faithful strict tensor functor from our strictification of the finite dimensional modules, the strictification of this new dynamical module category. So it leaves objects invariant, but it sends morphisms to this dynamical version of the morphisms, which we introduce as basically our morphism itself, composed with both non-dynamical and dynamical fusion operators. So the non-dynamical ones appear here, so conjugated with A. Now we get the additional dynamical fusion operators. And so what we've proven is in fact the following thing. If we have in fact any morphism A acting on the black strands, so acting on our finite dimensional modules, we can actually push this A through the red line. And what we get is this diagram that we have here, which we call the candy wrapper diagram, which is actually the dynamical version of this A. So we really see here that we have, so the ones here on the top and on the bottom, these are the dynamical fusion operators, and we have these non-dynamical ones composed with A, giving really rise to the functorial dynamical version of A. And as an additional notation, we'll say, okay, instead of always having to write these candy wrappers fully, we will just say that, okay, if we have a red box labeled by A, this is really the dynamical version of the morphism A. So this gives rise to a way of translating morphisms on the spin space, so on the black lines, to morphisms on the expectation value. So for example, one can do this with the braiding. So for braidings, we'll say, okay, if you have dynamical braidings, we will just depict them really as braidings, as overcrossings or undercrossings, but with this additional red dots to really visualize that they are dynamical versions. And so with this one can construct a dynamical R-matrix. So this was something that already existed. It was really defined so like this, like the thing that we have here on the right-hand side. But what we now saw is that, well, with this notion of dynamical braiding, this is actually just equal to our dynamical braiding composed with the flip automorphism, which is really which is a really natural thing to take as a definition. Due to, well, the way these braidings were also defined just in the finite dimensional case. So now the advantage of this graphical calculus with these dynamical R matrices is that, for example, the dynamical quantum Yang-Baxter equation, which was already known and which was proven in an algebraic fashion, now in fact follows immediately from the graphical calculus. Because what we have is, okay, we have here the two diagrams on the left-hand side. These are just the quantum Yang-Baxter equation for the finite dimensional modules. And we can push all of the braidings that we have here through the red line. So we get the equality between the two diagrams here on the right-hand side. And if we then translate this back to their algebraic meanings, this will actually immediately give rise to the dynamical quantum Yang-Baxter equation. So there's no more need to do algebraic computations to prove this. It just follows immediately from the graphical calculus. And then we can do the same thing, for example, for evaluation and co-evaluation. So there we'll also just put a little red dot to visualize the fact that they are dynamical. Here there's also, so the analogs of the dynamical R matrices here would be the elements called q lambda, which feature, for example, in Etingof Varchenko's work on these twisted trace functions. So there they just appeared as algebraic elements, but we now really saw that, well, yes, they actually are elements arising from dynamical evaluation and co-evaluation. So they don't just come falling from the sky. They are actually elements related to these dynamical evaluation and co-evaluation. And then finally, something about generalized trace functions. So the object that we actually wanted to study is graphical calculus are the ones that are defined as follows. So we take so this prime U to be a k-point vertex operator. We compose it with a Cartan element. So in this case, we take q to the power 2 lambda plus 2 rho. So we actually get two generic weights showing up here, so both mu and lambda. And then we take traits, in fact, over the Verma module and mu. So this is also something which is not trivial in the graphical calculus, because as I've said, we don't really have cups and caps on the red lines, but it can be shown that these traces are actually well defined. So as formal power series, these things can really be considered to be converging sums. So if we would leave out, say, for example, this cap, then this would give us something that really diverges. But if we take the full trace, so if we take both cap and the cap, well, then there's no problem with issues of divergence. So these are the basic trace functions. Now, the ones that should be studied are, in fact, normalized versions of this. And so the normalization that will work best for us is, in fact, the following one, where not only we have the vectors vi that appear as expectation values, but we also have these additional vectors fi, so additional dual vectors, which show up here with the trace functions in the right evaluation, together with, well, what we actually need is an additional dynamical fusion operator acting on these dual vectors. This gives rise to the following pictures. So we have our dynamical, so we have our trace functions. We have our dynamical fusion operator here on the top acting on the dual vectors, and I'm just taking a right evaluation to put both together. So these are normalized versions of the trace functions, and these were studied, in fact, by Etingof and Varchenko in their paper. So they are, in fact, they are not identical to the normalizations that they took in their paper, but what we can show is that they're actually completely equivalent in the sense that they will satisfy exactly the same Q difference equations. And well, this version of normalization is the one that fits best with the graphical calculus. Okay, so the equations that were proven by Etingof and Varchenko were the dual q-KZB equations. So where KZB stands for Nisnik homological of Bernard. So this is actually the quantum version. These are the quantum versions of the KZB equations that Jasper also showed last week. And so they can be interpreted as follows. So they actually tell us that, well, our trace functions are invariant under these operators, which are formed by compositions of dynamical R matrices together with these projections onto certain weight spaces. So these things will act on our expectation values VI. And on the dual vectors, we have this D operator, which is simply just a Cartan term acting on the dual vectors. So these operators actually give rise to a commutative system of q-difference operators. And so these equations were proven algebraically by Etingof and Varchenko, but the proofs are, well, require a lot of calculations, are actually rather difficult. So our contribution to this was, in fact, to give proofs that are purely graphical for the same equations. So what we start with is we start with something which actually does not yet involve trace functions at all. We just take compositions of k-point vertex operators together with these right evaluations. And we do the same thing as before. We say, okay, we put in the scalar, so q to the power like we had before. And then we say, okay, this reminds us of plugging in this twist elements, one twist and one inverse twist. So we can recognize this to be this thing precisely due to these topological operator q-KZ equations that we proved before. So these are just the plugging in the diagrams that we've proven before. And then we say, okay, we'll take this loop here on top. We can pull this loop all the way down through the red line here, and then we can pull it underwater. So we can really pull it through the red strand. And we do the same thing with the two gradings. So we get something like this. So we've really replaced this scalar q to the power by really something that now only acts on our expectation values. And then we'll take our boundary conditions. So we'll take a trace function on the lowest strand, and we'll take highest weight components on the top strand. Okay, so if we do this, then and we then apply the cyclic property of the trace. So meaning that, okay, we had these two strands labeled by V2 on the previous slide, and we say, okay, we can basically just pull this one all the way through the trace to the other side, so to get something right here. So then this gives rise to, well, something that can be contracted to a single loop acting here. And what is left in the blue, so as operators acting on the expectation values, is something which now still only contains dynamical R-matrices. And we get these additional crossings here, which precisely come from taking cyclic property of a trace. Okay, now there's still something left here. If we put q to the power xi as some marking, so we can still take any Cartan element here, then we see that what is showing up here is, it's a bit small, I assume, but it's here, but it says q to the power xi minus 2 lambda. So if we want to be able to still push this last loop also through the red strand, what we will need to take is precisely 2 lambda plus 2 rho. So this also, in fact, graphically tells us why Etingof and Varchenko actually took this 2 lambda plus 2 rho as these twistings, because these are the only ones that actually match with the graphical calculus to be able to contract a loop. And then if we do that, the only thing that we have left is really just dynamical R matrices together with the additional projection onto a certain weight space of V2. So this is then the short version of the proof of these dual q-KZB equations. We did something similar for Macdonald-Ruijsenaer's equations. So they are similar equations. They are similar q-difference operators under which the trace functions are invariant. But now they also involve, in fact, additional finite-dimensional modules W. So one can do this, in fact, for any W. So they also then give rise to a class of commuting q-difference equations. And actually what Etingof and Varchenko had in their paper were precisely these equations, but only for the case where j is equal to k. So only for the case where they actually put the Casimir elements on the rightmost position. And now, thanks to the graphical calculus, we were able to extend this, in fact, in one single proof to a class of difference equations, where, in fact, j could be any integer between 1 and k, so where the Casimir elements could be present in any position. Okay, and so this actually means that now, instead of this quantum integrable system, we've extended this to a super integrable system. The proofs are very similar, only now instead of the twist, so instead of the multiplicative Casimir, we now have to use the additive Casimir, so which is this omega W. So basically for any finite dimensional module W, one can construct such a central element in the quantum group. And so the proofs are very similar. I'm not going to give them in total, but the end result will be this kind of diagram. So the idea is that, okay, we have now, we can now just simply take two dual vectors here. We can, on this position, we can take an additional loop labeled by W, which would precisely be this additive Casimir. And then we can deform it in such a way that we can basically push it all the way through the red line. So to obtain it here. And so such that we are actually left with traces over W of just simply dynamical R matrices together with projection operators. Okay, I think that was everything I wanted to say. Yes, so I hope that I've given you a nice introduction to this this new way of performing graphical calculus. And so I will happily refer to my paper, which just appeared last week on the archive, and the part 2 is still work in progress. Okay, thank you.
Any questions, comments?
Maybe one question, Hadewijch. In your category, your new category, dynamical module category, what are the adjectives you can put on it? Is it monoidal? Is it does it a twist, or because your twist is different?
Mm-hmm. The dynamical module category. Yeah. That's a good question, actually. So it's not braided actually. So the dynamical braiding that we have is actually does not define an actual braiding on this category. So for the moment, it's still considered to be just a monoidal category. Although we assume that the evaluations might give rise to a rigid structure. I think there this could still be true, because what we have is that, well, you have these axioms for duality. We have these strands that can just be, you can just straighten them out, and this also still works for the blue strands. This also still works in the dynamical version, but for the braiding it will not work. There are actually no non-trivial braidings that one can define on this dynamical module category.
Could you choose the Verma module reducible? Because I think here it's
reducible, or
yes.
Yes, sure.
Do you have some new equations appearing in this case? Because in the quantum case, when I study spin chains, this guy becomes the Q operators, and you have the TQ operators appearing in this case. Do you have the same thing here? Well,
I think what will be a problem here is that maybe if your Verma module is reducible, then I believe your highest weight will probably no longer be generic, such that we don't really have this expectation value isomorphism anymore. So it will, I think in this sense, it will not make so much sense to write down the k-point vertex operator.
There's not any more questions. We'll thank Hadewijch again.